Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEM. The title for today's webinar is Tank, Silo, and Shell Modeling in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Wieland Goetzler will be your moderator, answering any questions you may have. He's a product and customer support engineer located in Leipzig, Germany. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the webinar. You can do so within this same dialog box. We'll do our best to get to all the questions, but if by chance we don't, I will certainly send you a follow-up email afterwards. So I quickly want to go through and explain the concept of our main program RFEM and the add-on modules, as well as what we'll be running through today within the next hour. So our main program RFEM is a finite element analysis program. This is where we'll be completely modeling our tank structure today. We can also integrate with BIM software such as AutoCAD, Revit, Tekla. We won't be doing this today, but there is that capability. We'll fully load the structure and we will run an analysis. Now with this analysis, you can get things like the design internal forces, stresses, support reactions, and you can take this analysis information into your own external tools such as Microsoft Excel, or maybe you have some in-house software to do the actual design. Now, in turn, you can also utilize our add-on modules within RFEM to do the design as well. So for example, today we'll be working in RF-STEEL surfaces. This will provide us with a steel surface stress and serviceability limit state design. Now this is for our 2D surface shell elements that comprise our silo structure. We will also utilize RF-STEEL AISC. This will provide us with the member ultimate and serviceability design per the AISC standard. And lastly, we will get into RF stability, and this will provide us with an eigenvalue analysis of our structure and provide us the different buckling modes under the applied load cases. So with that said, we can jump into RFEM. The first thing that we want to do when we launch a new file in RFEM is to give it a model name. And the type of model will be 3D. Now you can create the load combinations automatically according to the ASCE 7, for example. We have the Canadian standards and many other international standards. Now you can always uncheck this box to create those load combinations manually as well if you don't see a specific standard that you would like to generate them automatically with. And we can immediately jump into the program. So you can see here that we have our graphical interface window right here in the center. We have our tables to work with down here at the bottom. This will control all of our input data. Some engineers prefer to work with these tables, which we do have an import and export button directly to Microsoft Excel. Once we run an analysis, all of our results will be available in table format as well. We have our tools to work with up here at the top, and we also have our project navigator on the left. Now with the project navigator and specifically the data tab down at the bottom, well, this is going to provide us with all of our input data that we're going to see graphically here. You scroll down and you will see the long list of the add-on modules that we have available for design purposes or a little bit more advanced analysis. The display tab is going to control everything that we're viewing. So it's not going to have anything to do with the input data of the model itself, but rather how we're viewing maybe our results or what we want to show or hide within this graphical view. And lastly, once we run an analysis, we will also see our results available in this project navigator. So to begin with, I'm going to zoom in here to my origin, and we're going to create a line element. Now, instead of a straight line, we're going to choose this option here, a circle, and click on the origin and define the radius as 1.5 feet. So this is going to begin the modeling of the roof element within our silo type structure. I'm going to highlight this line element and we're going to use the move copy tool. We're not going to make any copies, but we're just simply going to move this in the 1.75 foot Z direction, the global Z direction. So going back to my line element, we're going to choose a straight line here. And this is where we can easily snap to that circle we just created, and we'll snap to a point down here on our drawing grid. So I want the overall roof to have a radius of 7 feet. So that's why in particular I'm snapping to this point 700. I'm going to take this single node here, and I'm once again going to utilize the Move Copy tool. This time I will create one copy, and I'm going to copy that node 0.25 feet in the global X direction and negative 0.25 feet in the Z direction. So what I'm doing here is I want to create a sort of curvature where my roof surface elements are going to transition into my vertical wall elements. With that, we will create a new line element, but this time we'll choose an arc. So when I snap to these 2 points here, and I want to change my plane local in the Z, then I can just define a radius of 0.4, and we get a small curvature here. So now that I have these two line elements defined, I'm going to hold down my Control key to select both of them and move on to my Rotate tool. So with our Rotate tool, we can make 8 copies here at 45 degrees, but we have a nice feature under the expanded settings. So real quickly, we will be rotating around the origin. You can easily change a graphical, or you can choose a point graphically to change that if you would like, but the origin is fine here. So under this expanded settings, we have the option to create surfaces between our copied lines. Now we don't have any existing surfaces, so we don't currently have a template available, but that's no problem. So once we click OK through all of this, you'll notice that all of those surface elements were created automatically as we rotated through this structure. They are highlighted red right now, and the reason why is because if I highlight all of these surfaces, I double click to edit them, the stiffness is set to null, and that's simply because we didn't have a template to choose from when we were in that expanded settings. That's easy enough to change by using this drop down to change this to a standard stiffness, and we'll define our first material within the program. So we have a couple default materials, but I want to move forward with stainless steel for today's structure. So over on the left, we have some filters that we can use, such as metal, stainless steel, and the ASTM standard. Now you can see this long list available here of pretty much every stainless steel material that you could probably use for design purposes. We can also utilize a favorites group here, which I've just added a couple materials, stainless steel materials that I'll be utilizing in today's webinar. Rather than sifting down through that long list, you can simply add them to your favorites list. So today we'll use the stainless steel A240. Here are all of my material properties given to me in this table below. I click OK. The next thing to do is to define a thickness of 0.2 inches. We click OK. So now when I click out of there, you'll notice the color has changed to indicate that we're using a stainless steel material. So the next thing to do is to select my circular elements up here at the top. I can zoom in and right click on this element, and under the line option we have Extrude Line into Surface. So by doing this option, I now have the stainless steel material defined here in the program, so I can choose stainless steel, and the height of this will only be 1 foot. Now the depth is where I'd want to determine what my thickness would be, and if we're just keeping this the same as the rest of the roof structure, we can choose 0.2. Now down here we have the extrusion direction, so you'll notice that this changes depending on which global z-axis or local z-axis I choose here. We will stick with the positive z-axis. I click apply. So now the wall elements to that opening have been created automatically. So that opening was easy enough to create, but let's say we're interested in applying another opening within the roof element here, and maybe changing this to plan view. We'd like to add in an opening over here on the left somewhere. Well, we do have this tool up here in our toolbar for openings. Now, openings can be pretty much any shape you would like, such as circles, rectangles, quarter circles. But keep in mind that this opening is only for coplanar surfaces, so surfaces that lie within one plane. And if we're looking at these surfaces for a roof element, that's not the case. They have curvature to them. So I can't just easily select a circular opening here. But we have some useful features within the program that will allow us to model a more complex opening on the left-hand side. So I'm going to go back to my line element, and I'm going to choose a circle. And we'll assume the opening is somewhere over here with a radius of 1 foot. Now, turning this back into elevation view, you'll notice that circle is just simply drawn on my drawing grid. I'm going to zoom in here, right-click on that line, and we have, again, the option to extrude the line into a surface. This time, I'll extrude it 2 feet in the global Z direction. I click Apply. Now I have those two surfaces modeled, but the problem is the program still does not recognize that they're intersecting. So how do we get it to do that? Well, I can select this surface that I just created for my second opening and hold down the Control key to select the roof element surface. I right-click, and we have this option here for Create Intersection. Now, this is a pretty powerful feature because now under the Data tab, and specifically if we go up here to our surfaces, well, here's all of our surfaces that we've created so far. And here are the 4 components that were automatically created with the intersection of our roof element surface and our opening surface. So now that we have the intersection components defined, what I'd like to do is to right-click, and under Intersection, we have the option to convert into a line. And back to the openings up here in our toolbar, we have the openings option by selecting a boundary line. So then I can easily just click on that line we created with the intersection, but you'll notice that the program still does not recognize that that opening is integrated into this roof element. Well, I can do so by double-clicking on the roof element, and under the Integrated tab, you have the option here to integrate openings within a surface by simply selecting it graphically. So I select that opening, I click OK. The program asks me it doesn't lie within the surface. Do I want to continue? Yes. And now you'll notice that that opening now exists. So we're almost done there, but we probably want to get rid of the surface elements below the opening. Well, that's easy enough to do. The first thing I want to do is to select my original surface here. I can click Delete, but you'll notice the boundary lines still remain. Turning this into wireframe view, I'm going to zoom in here, and we have a tool called Connect Lines or Members. And let me turn off my grid and make this a little bit more clear. So using the Connect Lines or Members tool, I can drag across that opening, and all that did was split this line into 2. So now I can select everything below the opening and delete it. So we'd like to go ahead and model that surface back in, what we originally deleted. Now, again, we have this option up here to create many different surface shapes, but these are for coplanar surfaces. This is certainly not a surface that lies within one plane. So for that, we can use the option for a quadrangle. Up pops my dialog box to define my stainless steel material. My thickness remembers my settings from last time is 0.2. I click OK. All I need to do is to click a single point. The program recognizes all of the boundary lines, and turning this back into a rendered view, we can see here that that second opening was modeled. So that really entails everything for the roof element. So let's move on to the body of our silo structure. I'm going to select this circular element, these lines down here at the bottom, and what we've already seen before, right-click, under line, we can extrude the line into a surface. This time we're going to choose something much higher at 38 feet. And I do want to increase the thickness here to something more like 0.32 inches. We probably have a lot of pressure from whatever we're filling this silo structure with, so we want to increase the thickness here. Now, again, you can choose the directions that you would like to extrude this, and it makes the most sense in our scenario to extrude this in the negative global Z direction. I hit Apply, and I can exit out of here. So now a bulk majority of this silo structure has been created. Down here at the bottom, I want to create a couple transition points. Now this will make a little bit more sense as we get further into modeling, but I'm going to highlight this bottom circle, right click, and once again extrude the line into a surface, but this time only 3.5 feet in the negative Z direction. And one more time with this bottom circle, extruding the line with a distance of 1.5 feet. Okay, so the next thing to begin modeling is our hopper. And with the hopper, I want to utilize my drawing grid again, but remember it was, if we turn this back on, it's way up here at the top. So we can easily move that drawing grid down here to our bottom of our structure by right-clicking down at the bottom of the screen on Grid and choosing Edit. Here is where we can specify the origin of that drawing grid, and I'm going to set this as negative 53.75 in my Z coordinate system. I also want to change the grid point spacings to something a little bit smaller, such as 0.5, and I click OK. So now that grid was quickly moved down to the bottom of our structure. So moving forward with the hopper, I'm going to select a straight line element that we have seen previously, and I'm going to snap to a point on my cylinder and zoom in down here onto my drawing grid to a point 1.500. Now, just like what we saw before, I'm going to highlight this line element. I'm going to use the rotate tool, 8 copies, 45 degrees, about the origin. That's great. Under the expanded settings, I want to continue to use this option to create surfaces between the lines. But now you'll notice that we have many different templates to choose from based on all of the other surfaces that we have defined. So I'm going to end up changing the thickness anyway, but it's great to be able to right off the bat define that stainless steel material. So I can choose any one of those templates. I click OK, and then the program will automatically create the hopper for us. If I'm at all curious about what's going on with the different thicknesses of my surface elements, under the Display tab, remember I mentioned this controls everything that we're viewing graphically here, I can scroll all the way down to the bottom. And here we can create colors in the graphics according to some different types. For example, the surface thickness. So now I can view my surface thicknesses as colors. I'll notice my roof is 0.2, indicated by this blue color. The body is 0.32. And my hopper, I'd actually like to highlight all of these, double click on them, and back under the General tab, we'll change this to a thickness of 0.3. And all of the colors are updated accordingly. So that really entails most of the silo modeling itself as far as the body, but the next thing I'd like to move on to is something called a ring beam. Ring beams, for our purpose today, will be utilized for transitions between our supporting hot-rolled steel members and our 2D surface elements. Now, ring beams can also be things like wind girders to provide a little bit more stiffness for those lateral loads. And you'll notice I highlighted these two circular elements at the middle point here and at the bottom. And I'm going to go up to my toolbar to create a visibility by selected objects. Now, if I zoom in here, I'm going to select this entire circle. I'm going to right click, and under the line option, we can set a parallel line. With the parallel line, we set an offset distance of 0.25 feet, for example, and we can set that according to the local y-axis of the line. So we can do that in either the negative direction, or in our case, we'll choose the positive Y direction. I click apply, and just like something you would see in AutoCAD, we've offset that line by 0.25 feet. The next thing to do then would be to draw a straight line element, and just choosing a straight line from our options here, we will choose to create small little straight segments on the left side of this ring beam and on the right side. I'm going to use this option to break apart those lines again by connect lines or members and just drag that over my straight line segments. And the reason for this is because I'm going to move forward by now defining a surface with this drop-down box here by selecting my boundary lines. This ring beam is in one plane, so that's easy enough to use one of these options, select the boundary lines. I'm going to increase the thickness quite a bit to 1 inch here. We're still utilizing this stainless steel material. I click OK, and now the program will allow me to easily select the boundary lines on the front side of our surface here to create half this ring beam. And you can see the first half was created. Now we'll do the same thing on the rear side of the structure just by moving around and selecting these boundary elements. The program will create the second half of the ring beam. For our bottom element, we will highlight it and right-click, underline, once again, choose Set Parallel Lines. This time I want to choose the negative Y direction by 0.25 feet. I click Apply, so the program has simply created those offset lines. And I am going to draw in my straight line segments, just like what we saw up above on the left side of the structure. And scrolling over here to the right side of the structure. Now I'm going to break apart those lines once again by just highlighting or dragging my selection box over the straight line segments. And just like what we did, we're going to choose the boundary lines. You'll notice the program remembers my settings of 1 inch thick stainless steel material. I click OK, and then I am going to choose the boundary lines for the front side of my structure. And the program will automatically create the first half of that ring beam, and we do the same thing on the back side. So just moving around the cylindrical elements here, the second part of the ring beam is created. Now, let's say that I'd also like to do that thing, but offset 0.25 feet from my lower ring beam in the other direction. Well, we could do that same process over again, but what's even a little bit more useful is to highlight my upper ring beam here. I can zoom in, hold down my control key, pick a particular point, and drag and drop. So the drag and drop feature is extremely useful if you're just wanting to make a quick copy. So you just hold down your control key and move it. Now the program's smart enough to recognize overlapping lines and nodes and will merge everything together for us. So now these surfaces will mesh together and we'll have full force fixity between both of them. So if we cancel out of this visibility mode, we are essentially done modeling our silo structure in terms of the 3D or the 2D elements. Now we want to move on to our supporting hot rolled steel members. For this, I will jump into my new single member and we'll open up our cross-section library, and up pops a bunch of cross-section profiles. So for today, we'll specifically be in this rolled section and the circular hollow sections. Now over on the left, again, I have my filters according to the various standards. We will choose the AISC 2014. And for my columns, I'm going to choose the pipes extra strong with a 10-inch diameter. We do need to add in a new material here. So I go back to my material database and I can activate my favorites group where I've already added this steel A53 grade B. Now again, you can use the filters over on the left that we've seen before. I click OK, and now I'm ready to begin modeling my column elements. Now we could utilize our drawing grid here and snap from 2 points, change the plane, but I want to show you guys some useful features again today that make our lives a little bit easier. For example, we can just easily specify the length and direction of this column as 8 feet for the length, perpendicular to the work plane in the negative direction. So now when I zoom in here and I just simply snap to a single node, the program will automatically determine the correct magnitude, or sorry, the direction and the length of these columns. So rather than changing around our work plane several times and snapping between 2 separate points, we can easily just model in these columns here with that application. So now that I've created these 4 columns, I can hold down my control key to select all of them. And again, utilizing this drag and drop, hold down my control key to make a second column stack here. Moving on to the horizontal beams, again, going in to draw a new single member, we will open up our cross-section library. And this time we'll utilize a standard pipe with a 3-inch diameter. We've already defined steel A53 within our model, so we'll always have that available now for any future members that we'd like to model. I click OK, I click OK, and here is where I can easily just snap to these points on my column to create my horizontal beam. We'll rotate around the structure, and it's picking up some snap points from the hopper, so that's easy enough to take care of just by rotating the view a little bit. Now, we can continue on by modeling our vertical braces here, and we would want to start off with choosing a snap point here close enough to our where our columns and beams intersect, and we can snap up here to a point where it intersects the 2D surfaces. Now, it looks like something's a little bit off with the geometry, but it's okay, no worries, because I went ahead and continued on with the modeling of these members. And just for time's sake, I think we understand the process here of creating new cross sections. So to open up this saved model, I went ahead and created all of these members for us. Now notice I have my vertical braces in here. I did offset them a little bit down below the surface just to avoid large forces being transferred into these surface elements. I also added in some stiffeners along the hopper to the silo wall transition. If I double click on these are just MC shapes, MC 10 by 41, but I rotated them around to make sure that the legs of this channel section are facing outward on my silo structure. So that's really just the concept that we have there. And then I've also added in some nodal supports. Nodal supports, line supports, and surface supports can all be found up here in our toolbar. You can double click on them to take a look at what we can define in terms of our translation and our rotation, our 6 degrees of freedom. We also have spring constants in here, so it's not always the case that we have a fully fixed or a fully released condition, so you can define those spring constants here for some type of partial fixity. Then lastly, if we do have any nonlinearities with our surface, line, or nodal supports, you can model them as nonlinearities such as partial activity, sliding. Those can all be taken into account. But for our simple application today, we'll be choosing the hinged nodal support. So we want to move on then to loading the structure. The first thing to discuss before moving on to loading is something called the local axes of our surface. If I right click and I show the local axes of these surfaces, every surface element has its own X, Y, and Z axis. Now this is lowercase, not to be confused with our global X, Y, Z of the entire model. So you can imagine that when we're placing these loads on the structure, we'd like to place them according to the local Z axis in the outward direction, for example, for a pressure. If we have our Z-axes facing every which way within this model, it's not going to make our life very easy when we go in to apply these loads to a whole set of members or a whole set of surfaces at once. So it's very important that we align all of these local axes to be in the same direction. You can see here the Z-axis is facing inward for our wall elements. Well, if I scroll up here to the roof, it looks like the same thing. The Z-axis is all facing inwards. This is good. But you'll notice that if I take a look at one of my surfaces here, and maybe we change this viewport. I'm going to highlight these two openings and create a visibility by selected objects. You'll notice that my Z-axis here is pointing outward. All the rest of them are pointing inward, so this is not good. How can I quickly make these changes when I have surface elements that do not align with each other? Well, for one, the Z-axis, that's easy enough to fix by right-clicking and reversing the local axis system. So that's a quick step that we have to simply flip the Z-axis in to out. So now that Z-axis is facing inward, but something else to discuss. So not only for loading purposes, but for our results, local axes are very, very important. Our results are going to be presented to us in terms of surfaces local axes, such as forces in the local X direction, forces in the local Y direction, stresses, and so forth. So again, if we have our X axes facing all whichever way directions, then graphically our results are not going to be accurate. We can see here that the X axes are facing in the vertical direction for our surfaces over here on the right, but on the left, the X axis is horizontal. So again, we need to make changes to this so that all of the local axes align. Now, reversing the local axis system won't work here. It's still going to provide the X in the horizontal direction. So a nice feature that we have is to select multiple surfaces. You can double click to edit them, and we have an axes tab. This Axes tab will allow me to align, for example, all of my local x-axes parallel to a line within my model. I can select a line within my model graphically, and I click OK, I click OK. Now the program automatically oriented all surfaces' local axes parallel to that single line. So you can imagine how beneficial that is when you have hundreds of surfaces going in every which way direction, that we have a nice feature there to align them all at once. Okay, so now that our local axes are taken care of, we can move on to loading the structure. I'm going to right click to turn off the local axes system, and we can move forward by creating our first load case. So I'm going to go up here to my edit load cases and combinations and create a new load case. Now for today's example, the loads are going to be very, very simple. It's just for the sake of time to give you an idea of what exactly we can do in terms of the loading, but very brief. I won't even apply external loads such as wind or seismic today. I do hope to do a future webinar on a structure such as this to really get into much more detailed analysis of the wind loads on this structure. So we'll just keep this as general fill pressures from the inside as well as self-weight. So the first one will simply be dead load, where we'll be activating this self-weight here, and that will be the only load that we apply to for this particular load case. I create a second load case, and this one's going to be my pressure created from the fill inside, and we'll call this one horizontal pressure. So it's going to be normal to our surfaces. The action category, we want to change this to something like live. It could be fluid, just depending on how you prefer to do your design of your structure. Now, the action category is important, though, because this tells the program how to assign the applicable load factors from the ASCE 7 to each individual load case. So starting off with this horizontal pressure, I click OK. I make sure that that's what's available here in my drop-down box, and I move on to applying my first surface load. So I open up this dialog box here called New Surface Load, and the first thing to notice is that the program asks for the load direction. Well, this is where we're going to specify that local Z direction. I do want the load to vary linear in the Z direction. And the program says, okay, well, I can vary it linear in the Z direction, but you need to tell me where exactly I need to do that. So this is where we select 2 points graphically. So I'm going to select a point way up here at the top of the silo structure, and then way down here at the bottom where it transitions into the hopper. Now at the top, I'd like to have a magnitude of something like -0.5. But down at the bottom, we want something much larger, because obviously as the depth is increasing, then so is our pressure. So here is where we can choose something much larger, -0.5 kips per square foot. I click OK. Now I choose the surfaces graphically that I would like to apply these surface loads to. So you can see that horizontal pressure displayed internally within our structure. It varies linearly in the Z direction, and it is applied only to those surfaces that we have selected. In a similar sense, we're going to go back to the surface load here, and I'm going to do the same internal pressures for the hopper now. But this time, we need to choose 2 different locations in terms of our varying loads. So we're going to choose at the top of the hopper and at the bottom of the hopper. So at the top, maybe we have a magnitude of -0.2, but at the bottom, it dissipates to 0 kips per square foot. I click OK, and then I can graphically select these surfaces, and now you see that outward pressure displayed within my hopper. Moving up to the roof, which is very interesting because we don't have this symmetrical structure like we did with the hopper and the walls, but instead we have the openings here, we have these smaller walls for the openings, we have some curvature for our roof. So how do we quickly take all of this into account? Well, this is where we would want to apply a load, but in particular something called a free load. Today we'll be working with a new free rectangular load. The first thing I want to do is the program asks, well, which surfaces will I apply this to? And this is where I can graphically select all of my roof surfaces here. I click OK, and I'm going to apply it again in the local Z direction. And the projection of the plane of load, we will select the YZ plane. Now, once again, I want it to vary in the Z direction. Maybe at the bottom, I would like it to have a negative 0.5 kips per square foot. And by the time we get up to the top, the pressure is going to be 0. The last thing to do is to define my rectangle. So I can define that rectangle by turning back on my grid point. We're going to rotate the structure here. And something interesting to note about this is that it really doesn't matter how I define my rectangle. I've already defined the surfaces I want to apply this to. So as long as my rectangle encompasses those surfaces, you'll notice that I clicked 2 points way outside the structure here. So once I click OK, then you'll notice that the program creates this rectangle around my roof elements, and this outward pressure is being applied to all surfaces, including these smaller wall elements for my opening. Freeloads are incredibly powerful for structures that really don't have a lot of symmetry to them, or just anything really complex going on. So again, we can utilize those type of features. So we're pretty much done with the horizontal pressure. Perhaps I would like to show some type of friction loads. And for my friction loads within the inside of this silo structure, I'm going to create a new load case, but I'm actually just going to go back to my load cases and combinations. I'm going to take this horizontal pressure and make a complete copy of it. So not only am I copying the text here, which will change this to vertical, but I've also copied all of those loads that we just created. So why would I want to do this? Well, when I click OK, and over here in my project navigator, we'll jump to the data tab, we'll scroll all the way up here. I have my loads tree. And if I expand my loads tree, I'll see LC1, my dead load, my horizontal pressure, and now my vertical. I expand this even further, and here are my surface loads. So my first surface load under this load case 3 is within the walls of my silo. I can right click to edit them, and up pops our same dialog box. We can easily change this to the X load direction. So this is the local X axis now. And I can keep all of these points the same, but what I do want to change is the magnitude. So maybe at the top I have a magnitude of 0 for my friction, but down at the bottom I have 0.5 kips per square foot. And we'll keep that as positive. I click OK. So now the program just automatically converts the magnitude and direction. I can zoom in here and see these small arrows pointing in the downward direction. We'll do the same thing for our hopper by right-clicking. You'll notice it's highlighted within the graphical view. I click Edit, and we'll change this to the local X direction. The magnitude here will be 0.5 to 0. I click OK, and now that friction load is applied in the vertical direction to our hopper surfaces. For our roof element, maybe we're not so concerned with friction up here, so we can just grab onto this rectangular freeload and click the delete button and get rid of it altogether. So that's really all that I want to cover in terms of the loading today. I know it's pretty simple, but just to give you an idea of what's going on. Going back to my load cases and combinations, the program will automatically create the LRFD and the ASC load combinations for us, and under the Load Combinations tab, we can see those individually. So here's our LRFD and our ASC load combinations. Now, before we move forward with our first analysis, there's just a couple other things we need to check. The first one is I'm going to highlight all of my members here. And you'll notice I even highlighted surfaces. That's fine. I right-click to edit the members. And I just briefly want to touch on the modify stiffness. So I am going to design these hot rolled steel members according to Chapter C within the AISC standard, which is the direct analysis method. Well, that requires a stiffness reduction factor, tau sub B, to be applied, as well as a 0.8 factor to be applied to our flexural and axial stiffness. So I did a complete webinar devoted to steel design, and I go into much more detail regarding this, but for today, just know that we'll just quickly touch on this, and that's how we're designing to. So refer to our YouTube channel if you do want to review that webinar in much more detail. The other thing to take a look at under Calculate and FE Mesh settings is our global FE Mesh is set to 1 foot. So if I click this option, Regenerate FE Mesh, I click OK, the program will automatically generate our FE mesh for us. So we never have to worry about tying it into lines, to members. Everything is generated for us based on that FE mesh setting of 1 foot. But if we scroll up here to the top and we take a look at our surface for our second opening, this FE mesh is not good. We have very thin triangular elements here. This just simply isn't ideal, which tells us that our FE mesh settings are too big for a surface like this. So what I can do is I can highlight these smaller surfaces here by holding down my control button. I can go down here to the bottom of my hopper, hold down my control button to do the same. And if I right click, we have the option under surface to generate an FE mesh refinement. We'll create a new one here. And this is where we can set a different target FE length. So something like 0.2 would be fine. Now I click OK, I click OK. This FE mesh refinement symbol is now shown on these particular surfaces. I go to calculate, generate FE mesh, and the program will update the smaller FE mesh for these surfaces. Now it transitions nicely back into my 1 foot global mesh setting. Same thing up here at the top. You can see this FE mesh looks quite a bit better. Now I also added FE mesh refinements about my nodes here, where I have these channel sections framing into my 2D surface element. So that's about that single node right there. If I double click on this, I can take a look at just purely where you define a radius about a node and the FE length on the inner versus the outer of the circular sphere element. So that's what's going on there. FE mesh is obviously very important in terms of a finite element analysis program. So now we are finally ready to run our first analysis. So maybe I jump down to load combination 3 here. And all of my loads are shown with the applicable load factors, and we can begin our first analysis. The program asks, should I go ahead and begin the calculation? Yes. And we will run through the nonlinear, taking into account P delta effects for this load combination 3. So after this, we can turn off our loads. Our results are displayed within the project navigator, as I mentioned before. Here's where we can take a look at the various deflections, for example, of the structure. We can also take a look at members. For example, maybe we're interested in the axial forces here of our steel columns. And lastly, we're probably interested in our surfaces as well. So our surfaces, as you'll notice, we can view the basic internal forces, again, according to the local axes. That's why I mentioned that's so important. But we also want to take a look at our stresses. So here you can see our long list of stresses available for our surfaces, whether that's shear stresses, normal stresses, principal. Most important is probably von Mises. So when I turn on my von Mises stresses, you'll notice that it looks like we have some hot spots here. So this really is probably a singularity issue. You know, we have very high stress concentrations about this single node. It looks like the stresses are at 53.28 KSI. But there's something very important that I want to point out in terms of viewing your results graphically. Back under the Display tab, and if we scroll up to our results, we expand out the surfaces tree, and we have this option for distribution of internal forces and stresses. Well, the default is continuous within surfaces. So this means that the program is using a nice smoothing algorithm to tie all of these internal stresses together for our FE elements so that we have a nice pretty picture to display here in terms of our contours. Now, this is nice maybe for viewing purposes, but what we would rather change this to is constant on elements. So now you'll notice things don't really flow together quite nicely, but what's happening if I zoom in is that each FE element has its own value. Then we're basing the contour colors on each individual FE element rather than trying to average them all together with the smoothing algorithm. You'll take a notice too that my stress went down from 58 KSI now down to 34. So you can see how this is incredibly important for how you're viewing your results. You may be over designing something if you're not viewing it correctly within any finite element software. So now that we have displayed our stresses here, the last thing I just want to mention in terms of viewing our analysis is, of course, something like our support reactions, if we wanted to do a further foundation design. And again, everything is available within our table format here. So the next thing to move on to is our first add-on module. So I want to make the clear distinction here that we are jumping into an add-on module within RFEM, and that will be RF-STEEL surfaces. So this is the add-on module. It's nothing more than a dialog box. All of our information, loads, load combinations, materials, cross-sections are all brought into these add-on modules. So I never have to redefine any of that information. But what I am going to do is just to give it a little bit more information for my stress ratio check. The first one to notice is that it asks me which surfaces do I want to design. Well, I can either check the all checkbox here, or I can graphically select just a few surfaces, whatever I would like. We can check all surfaces for this particular scenario. The ultimate limit state combinations I'd like to choose are my LRFD load combinations. Now we can also check deflections for these steel surface elements. So this is where we would choose our ASD load combinations. Then we simply move down the list. Materials, again, are brought in from RFEM. We can see here that the stainless steel material properties are shown. That's all that's applicable for these surfaces that we'll be designing. Under surfaces, this is where each individual surface is listed. Now we do have the option to even optimize these steel surface elements. We can optimize based on the thickness. So if I choose one of the optimized checkboxes here, you just give it a range between the minimum and maximum thickness and the increment that you would like it to go by. So we'll maximize or optimize based on our stress ratio. Serviceability data. Well, this is where I can graphically select all of my surfaces here, and I click OK. Now the reference length is going to be the most conservative value. So it's going to take one of these sides of the surfaces and use the most conservative value, which in our case are these long surface elements, which are 38 feet. Ideally, we'd probably define, I don't know, maybe the roof surfaces separately, the walls separately, the hopper separately, which you can do so in each individual line here. But for us, we'll just move forward with a reference length of 38 feet. So the question is, what are we comparing our serviceability deflections to? Well, under the Details tab and Serviceability, here is our limiting deflection ratio. So you'll notice there are three options here. Don't think too much into this, just pay careful attention to the characteristic. Now, the reason why we have all three is under the General Data tab. You can switch, but this is all based on the characteristic, frequent, quasi-permanent, based on the Euro code. So for us, we're just sticking with characteristic, which is why under the Details setting, we're only concerned then with this deflection ratio. So you as the user can control the L over 300, L over 360, whatever you would like to choose that for simply supported and for cantilevers. Under the Options tab, just like what we talked about in RFEM, we have this exact same option here within RF-STEEL surfaces. Do we want our stresses brought in from RFEM as constant on elements or continuous within surfaces? We want to choose the constant on elements here. This is a more accurate application for designing our stress ratio for our particular case. So we click OK, and we can begin our first calculation. Now, keep in mind that I didn't solve for all my load cases and load combinations back in RFEM. So that's what the program's doing now. I went back into RFEM. It's solving for the three individual load cases and all of my load combinations. It's bringing those stresses into this add-on module and comparing it to our capacity stresses simply based on our stainless steel material. And after these results are ran, we'll be presented with our stress check. So now our results are available in table format here. We can view the stresses by load case, for example, the stresses by material, or the stresses by surface. What's a very useful feature is you'll notice that as I'm scrolling through this table, the program will automatically sync it in the background here to show me exactly which surface I'm looking at. This big red arrow is showing me where the internal force or the internal stress is controlling. and the load combinations automatically updating within RFEM itself. So you can imagine that's very user-friendly for a huge model where you kind of want to understand where these high stresses are coming from. If we take a look at our material, for example, we are overstressed. We have a check of 1.18. So if I take a look at this, and maybe I jump to my graphics view, we can zoom in here. Now, keep in mind, I'm still in the RF-STEEL Surfaces add-on module. I am viewing my results graphically within RFEM, but technically we're still in that add-on module because you can see the RF-STEEL surfaces. So now in my results, it should look slightly different. Here are all my stresses presented to me, and here are all my stress ratios. So stresses just come from RFEM. My stress ratios, maybe if we jump to the von Mises stress check, again, we have these areas of singularities. This just means if we turn this off into wireframe, maybe we turn this into wireframe here, and I'm going to jump to my display tab to turn off my FE mesh. Maybe I'll turn off my FE mesh refinements. Well, these beam members here, beams and columns, are framing into these 2D surface elements at one teeny tiny little point, and that's this node. So all of these forces are being applied at this single node point. So when I look at my results here on my structure, this is telling me that all the stresses around this area are fine. So we probably have an issue of a singularity where we'd like to distribute the load at these locations a little bit better. So how can we do that? How can we take care of these singularity hotspots? Well, how we can do that is with something called an average region. So back under the data tab, and if I collapse my loads here, we'll be able to see this a little bit better. We have an average region. So what I'd like to do is to change around my viewpoint here. I'm going to turn off my results. Maybe I go back into a rendered view just to make sure I'm at the right location. And if I right-click under average regions to create a new one, the program asks, okay, well, which surfaces should I average out these internal forces and stresses? Well, we're going to start off with this location here, these two surfaces where one of our singularities is occurring. Now, the interesting thing is that we can project into these average regions through a global axis. So this will make much more sense in just a minute, but I'm going to choose the exact same surfaces on the opposite side of the structure. So now when I click OK, the program asks, well, where should I apply this average region? We want to click a single point here. So we'll zoom down and click the center. And we want to choose a circle, for example, with a diameter of 2 feet. This we want to project through the global x-axis, and it's going to average out the internal forces according to what the dialog box tells us. So I click OK, and now we can see this average region symbol shown for us, both on one side of the structure, but also you can see it on the other side of the structure. So this is just a quick way to apply average regions to both sides, or you can apply them individually. So if we go back to our results for RF-STEEL surfaces, we jump to RF-STEEL surfaces, the add-on module. Under the Details tab and Options, you do need to check this checkbox where it says Apply Smooth Internal Forces to define average regions. I click OK. The program's asking me to recalculate. Yes, that's fine. So all it's doing is taking those internal stresses and forces and averaging them out. So what I'd like to do then is you'll still notice that we're overstressed. That's because we didn't take care of all options, but jump to the graphics view. So for this, let's jump to load combination number 3, and let me turn back on my FE mesh to make this a little bit better. Going back to the results, we're going to show our equivalent von Mises stress and take a look where we applied that average region. We no longer are overstressed there. There you can see the average region indicated, so we're fine. So just something interesting to note that's how we can deal with singularities. I scroll around to the other side of the structure, same thing. Those singularities still exist in other locations. So what I've done under a saved model here is applied those average regions to all those singularity locations. So If we turn this into wireframe view here, I've even applied it to the locations of our ring beams to distribute that load or to average out that load where those channel sections are framing in. So now if I go back to the rendered view and maybe I take a look at my RF steel surfaces, I jump to that current module. Now we'll see our code check is at 0.92. So I didn't touch anything to do with adding more members, increasing the thickness. All I did was simply average out those singularity spots. So that's a nice feature that we have to not overly design this structure. Displacements, moving down there, these are just our deflection checks. We're at 0.2. So deflection is obviously not an issue within the model. The parts list is a material takeoff. So with that said, we are done really designing the surface elements of our structure according to a stress ratio. So moving on to RF-STEEL AISC. Well, this module should look very similar to our RF-STEEL surfaces, and that's because most of our add-on modules look almost identical. Same process here. We want to first define the members that we would like to design. So what I can do is to simply rotate my model, and maybe I'd like to define or to design just my pipe members to begin with. I click OK. I choose my AISC code here from my drop-down box. You will notice we have added the 2016 code in. We will stick with the 2010 for today. The ultimate limit state design, I can choose my LRFD load combinations, and my serviceability, we can choose our ASD load combinations, just like what we did with our steel surfaces. Now we move down the list. So our materials, A53 grade B was brought in from RFEM. Our cross sections were brought in. We can optimize here with this drop-down box as well. Intermediate lateral restraints, this is top and bottom flange compression restraints. We won't be dealing with that today with our pipe members, so we can leave all of this as is. The effective lengths is strong and weak axis buckling, torsional buckling, and for this, because we are designing per Chapter C, the direct analysis method from the AISC, we can leave our effective length factors equal to 1.0. The unbraced lengths will default to the full member length. So for example, this is why I created 2 column stacks here, so that the program will refer to the unbraced length as 8 feet as opposed to the full 16 feet, because I felt as though the strong and weak axis was braced okay with the addition of these horizontal beams. Torsional buckling, same thing. Now, lateral torsional buckling is not applicable in this case for these pipe members, so that's why it's grayed out. Design parameters, just a few more variables to take into account with our AISC design. And lastly, serviceability, same type of concept. We can graphically select our pipe members here by just choosing the viewport or the view box over those pipe members. The reference length will default to the full member length, and under the details tab, once again, this is where we can control our serviceability deflection ratios. We click OK and we can run our calculation. It looks like everything passes just fine according to the AISC in terms of our ultimate and serviceability limit strength, with our highest check being 0.72. So we can view the design by load case, by cross section, or by member. Again, it's synced up quite nicely to our RFEM picture in the background. The red arrow is pointing to where that controlling internal force that's being used for the code check is located. What's nice is that for a single member, member number 11, for example, we are giving you all code checks within the AISC, Chapter E, F, G, and so forth. For each individual code check, we have all of the given variables down here in our table, even information on whether this is slender, whether this is compact, and so forth, along with all of the code references of where these equations come from, so that we can ultimately determine our design ratio for this particular chapter. A parts list by member, again, the material takeoff. So we can also view everything graphically. We are within the RF-STEEL AISC add-on module, so this is where we could view our ultimate limit state code checks graphically, or our serviceability. realistically, I know I flew through that, and the point being that I do have a previous webinar, once again, as I mentioned, dedicated to only AISC design, where I go into much more detail. But it's nice to know that you can design an entire industrial structure within one model. So you can design these steel elements according to a stress ratio, but we can also get design of members per the AISC, for concrete ACI, if we ever have any aluminum members, and so forth. So the final add-on module I want to touch on is RF stability. RF stability, if we launch this, once again, just a typical dialog box. This one looks a little bit different. Here is where we're going to run an eigenvalue analysis for our structure. And what this eigenvalue analysis is going to tell us is the various buckling mode shapes for our structure. Now, whether that's related to the members or even the steel plates. So the default here is 4 eigenvectors to be solved for, but we can quickly change this to 10, for example. Now, the next thing to define are the load cases or load combinations to import in to be used for this eigenvalue analysis. You'll see here our load cases and combinations are listed. Now, something like our load case 2 with our horizontal pressure, this is not ideal. And the reason why is because a horizontal pressure is going to place a lot of tension on our surface elements. Well, tension doesn't necessarily lead to a lot of different buckling mode shapes for our structure. So what would be more ideal is axial load. So something like our vertical pressure, for example, would be more useful for our eigenvalue analysis for buckling. Now, the rest of these options, I'm going to leave them as default, and I won't get into them today. You can always click this little help button in the lower left-hand corner to bring you to our manual that will explain a lot of these checkboxes and options in quite a bit more detail. We will run an eigenvalue analysis according to the method by Lankos, and we can click calculate to run that calculation. Now, I already have this saved here because it does take just a second to run, not too long, but for the sake of time today, because we are at the end of the webinar, I have already solved for it. So here we will open up back our RF stability add-on module, and this will pull up our results tables. So you'll notice here that our critical load factors are initially listed. So our critical load factors are simply the factor that you can apply that load, so in our case it was LC3, before we're going to see failure of our structure according to these different buckling modes. So here are the 10 buckling modes I've solved for. The critical load factors, the ones we should be most concerned with are these smaller values here, and then we're least concerned with maybe these higher values. The magnification factor is just nothing more than a relationship between first and second order moment. So this alpha factor times our first order moment is going to equal our second order moment. We can also view the effective lengths and critical loads for our members. So this is quite interesting because once again, for a particular member, member number 1, we have our 10 different eigenvectors that we solve for. We're given the exact effective length here and the effective length factor. So if we were designing per the Appendix 7 within the AISC and we wanted our exact K values, we can actually import these in from RF stability into RF-STEEL AISC for an exact K value. So something very useful if you still prefer to do design per the effective length method. The critical load is going to be the max load that these members can take before they're going to experience the buckling behavior based on these different eigenvalues. And again, we can take a look graphically as the program will change that in the background. We can also view eigenvectors by node, by members, and by surface. So with all this said, if we jump into the graphics view, this is probably what's going to be most interesting to us. Again, we're in RF stability here, and under our panel, we can jump to the different eigenvectors solved for. So you'll notice my first 3 eigenvectors solved for are purely buckling of my members down at the bottom of my structure. And the same goes for the third. It looks like more of a flexural torsional buckling of these members down here. Our whole structure is twisting, so to speak. But when we get into maybe the 4th eigenmode, then that's where we start to see buckling behavior of our steel surface elements. So you can see the local buckling here right above our channel member. Maybe if we jump down to the 6th eigenmode and we circle around our structure here, again, this is where we're seeing this buckling behavior of these surface elements, and we even have some internal buckling on the other side of this. Jumping to our color panel, this is an eigenvector. It does not have any magnitude. It does not have any direction. It's just purely to give you an idea of the buckling behavior of the structure that could occur if you continue to increase those axial loads based on those critical load factors. So, jumping back to the table here, if we had critical load factors that were down around 1, 2, 3, well, that should flag us that we immediately need to pay careful attention to the structure at those buckling locations to maybe add in more stiffeners. Maybe we need to increase the thickness of our shell elements in order to prevent any type of buckling behavior that could occur. And you can imagine that this is only for this friction force, this small little friction force. So when we're adding in all of these other forces to take into account with the probable buckling behavior, that it really could be a huge influence on how we design our structure to prevent such failures. One other thing to just mention before concluding this webinar is under the Data tab, we do have another add-on module called RFEM. RFEM is very powerful because what we can do here is to import one of those buckling modes from RF stability. For example, if we're interested in the eigenmode number 6 from RF stability, well, we can import that in and we can actually pre-deform the initial model. So what does that mean? Well, we'll take that buckling shape from eigenmode number 6, we give it a value, a magnitude, and a direction, so maybe something like 0.2 inches, and we can generate the pre-deformed FE mesh. So once we click generate, then the program will come up with all of the FE nodes that take into account this possible buckling shape of our structure, and they are all listed here, every FE mesh element. So what's interesting about this is, why would we want to do this? Well, in the AISC, for example, one of the options in Chapter C is the direct modeling of imperfections. And with this, we can take into account, if this surface wasn't manufactured quite properly, we want to add in these imperfections before we run our additional static analysis, and you can do so with the RFEM add-on module. So again, I did a previous webinar different from the one I mentioned before. It's called Advanced Steel Design, where I do this whole process importing in RF stability into RFEM, and then we take that a step further with adding in some additional static loads to run our analysis. So if you are interested in that, certainly let me know, and I'll be happy to send that to you and show you where that's at on our YouTube channel. So we can conclude this webinar today. I know I flew through this information. This webinar will be recorded and posted on our website. You can also find out more information on these add-on modules in RFEM at our website, dlubal.com. As you heard me mention many times today, we do have several social media sites, including something like our YouTube channel, where we have all of these previously recorded webinars. So feel free to visit those if you are interested in further design according to steel, concrete, aluminum, glass, and so forth. Our email here at our Philadelphia office is info-us@dlubal.com, and our phone number is 267-702-2815. So by all means, if you have any questions on what you saw today or anything else, feel free to contact us. We will have many more upcoming webinars. I try and do them about once a month. You can register on our website at dlubal.com under support and learning and webinars. As most of you know today, I do send out a couple email reminders before these webinars come up. So keep an eye out for those. Now, as far as PDH credit for today, that's no problem. Many of you would like a certificate for that. If you could just send me the request at info-us@dlubal.com. That is info, INFO-US@dlubal.com. and let me know who was in attendance today for the webinar, and I can issue those certificates individually and email them back to you. And with that said, I want to thank everyone for attending the webinar today. As always, we hope to see you at the next one. Thank you.